Alright, everybody get ready to get going? How are y'all doing? Did you have a nice weekend? Okay. Let's see here. Maybe some people are missing from the rain, but there's 1, 2, 3, 4, 5, 6, 7, 8. Alright, so 22 people. I think we're ready to get going. That's a couple minutes after. Okay. So we're going to be talking about the vision chapter 10 this week, right? Yes. So I'm hoping you guys are prepared. Got a couple ideas of some questions that didn't make sense from the chapter, maybe? Yeah.
I guess just a little more on the horizontal and amateur cells. Are they just to aid moving the neurotransmitters along or aid in the connection between the bipolar and everything?
Yeah, really good question, Constance. So if anybody didn't hear, sort of talking about those horizontal and amacrine cells, kind of what exactly are they doing? What's their job? What's their role? We're going to dive into that. So the idea, right, and we'll look into this sort of basic, simplified neural network in the retina, right? So you're going to have your photoreceptor layer, you're going to have these bipolar layers of cells, and then you're going to have this other layer of the retinal ganglion cells. And in between those layers, you have this thing called sort of lateral connections through these horizontal and amacrine cells. So basically, what they're going to help to do is not send information, what you might conceptualize as vertically, sort of through those layers, but across those layers. And so we'll talk about the role that they play with different neurotransmitters. Really, really good question. We were going to dive into that in depth. But the big sort of idea with those kind of cells is that they're going to be doing not just lateral sort of connections across different cells in those layers, but importantly this idea that we'll dive into called lateral inhibition, which is the idea that you can inhibit your neighbors from talking, essentially. That is, when you want to amplify a signal that you need to say, so let's say you ask this question in class, let's say that this is one of those classes where everybody's talking. I don't know, there's a lot of, and you want to make sure your voice sticks out in the crowd. When you talk, you might tell your neighbors around you to shh, so that your voice sticks out. That way you can be heard. And that's kind of a simplification of what this process of lateral inhibition is going to do. And we're going to get into the nitty-gritty of it, but that's a really good way to start thinking about that stuff. So that's a really good question. So we're going to be diving into that. I'm going to try to cover some stuff today, introducing the chapter, introducing the content, and then I want to start pivoting, particularly Wednesday, next class, to start sort of trying this idea of sort of this flipped classroom idea, where we can start having some student presentations, maybe some debates, maybe some discussions, and having people kind of responsible for presenting some of the figures from the chapter. Does that sound pretty good? So fair warning for Wednesday. Okay. Maybe we'll get to this towards the end of the class a little bit. We'll start assigning maybe different sections of the chapter to different groups. Does that sound like an idea that might be fun? Okay. We'll give it a shot. Okay. So before we do that, let's see here. So, was there anything you guys wanted to go over from the test last week? Any questions? Any really bad questions that were on there? Things that maybe you think were marked wrong and they shouldn't have been, or anything like that? Like, we can change that stuff around. Yeah.
The EEG question kind of threw me off because it said rhythm, and then epilepsy is also defined as like rhythm in the brain. So that threw me off.
Okay, let's see if I can find that EEG question. Let's see here, the EEG question.
Oh, it said like brain scan or something like that.
Yeah, give me just a moment. I will bring this up.
There's one with the neuron doctrine too.
Okay, we'll take a look at that one too. Where is... So I should say too that I'll probably be reaching out to some people because I'd like to learn a little bit more about what your experience was with the tests too, as I kind of bring up some of the, I'm going to sort of dig into this, but several of the tests were actually submitted, so we get timestamps of the tests, and I could tell that people submit them after they left the class. So we'll be looking into that. So I really want to learn about your experiences, about how that could have happened. So if it turns out that there's something going on that maybe shouldn't be, then there's some pretty easy steps we can take to accommodate that. It's the beauty of these digital exams. I get lots of data back. So I really welcome any feedback you guys might want to have in discussions about that. We'll probably switch some things around next class. So we probably won't allow any questions to go back. Probably only one question at a time, which are relatively minor sort of changes. But if we see those changes come up, it's going to be some of the reasons why. Okay? Okay. So let's see here. What could be... So, where's our test? I'll be up here in just a second. So you wanted to find EEG, right? Or rhythm?
Yeah, it's a
Or
rhythm.
epilepsy. So is it this question? Spontaneous rhythms that can be recorded from the surface of the scalp?
Yeah, it is that one.
Okay. So what we have here is, it says spontaneous electrical rhythms that can be recorded from the surface of the scalp. And the correct answer is that, very simply, they're generated by the activity of populations of neurons. Which is kind of that conversation we had at the end of the last class, about how this EEG activity is representing the activity of millions of these neurons. We talked about convergence and divergence, and it brought us to that conversation about these electrical signals at the scalp. That's why this is the right answer. Are you asking if this was the right answer?
That's what I chose because
Yeah.
the definition of epilepsy had rhythm in it, and I thought it was confusing.
Yeah, so it does have the word rhythm in it, but that doesn't mean that this is that's necessarily right. So all this is spontaneous electrical rhythms that can be recorded on the surface of the scalp. So you have spontaneous rhythms of your brain right now that we can record from your scalp. And just because you have them doesn't mean that you have epilepsy. In fact, it's actually pretty normal. If you didn't have them, you'd be flatlined, which means you'd be dead. So, just because you have them does not indicate a pathology such as epilepsy. And that's why that's the wrong answer. Does that help? Yeah, sorry. So it's really, and this is kind of what I was trying to explain from the beginning of class and then a little bit setting up for the test last class we had, is that when in doubt, keep it simple. That, this is sort of one of those like straight down the pike questions where it's just asking a simple thing. It's made by, millions of neurons, right? Those EEG signals. And so A really good strategy that we can use in sort of solving a lot of tests, not just this one, GREs, MCATs, SATs, whatever. If you're ever in doubt or struggling, think about what answer you can't get rid of. Say it again, said it another way. Start ruling stuff out and say, is this just generically true? And if it is, then it might be the simplest, easiest solution. Does that kind of make sense? Yeah.
I know B's wrong, and I'm not gonna like, cause
Yeah.
it's for sure wrong. But is it wrong because the wording of it's like it's moving, rather than they're firing?
That's a key factor. Yeah,
Okay.
so the word moving here is definitely one of the key parts about it being wrong. So yeah, I mean, so neurons, they don't always move, right? They're, oftentimes they might be kind of like stuck in place. But you're right, they can be firing or they could not be firing, right? We hope that there's times when they are and there's times when they're not, so it's not just constant pop, 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 because they need a break. But yeah, so these are spontaneous rhythms. They do not demonstrate that the neurons are constantly moving because it's not the movement of neurons that elicit this electrical activity. Yeah, really good question. Good insight. Any other questions on this one? Yeah.
So I understand why A is incorrect, but what would be like the definition of epilepsy since it's like spontaneous electrical rhythms? Because isn't that epilepsy, or what would like the correct definition of epilepsy be?
So, we have that in the text in the slides at the specific semantic level of what the epilepsy stuff is, but generically speaking, right? You guys remember we talked about epilepsy being that sort of overactive activity? Remember the slides we looked at where you have the kind of normal rhythms and then it goes because you have the seizure? Be that overactive.
So that like if it said overactive spontaneous electrical rhythms, that would,
Yeah.
okay.
Yeah, so, if anybody has a, and I mean, you can go dig out the specific, definition, but, yeah, the idea, the big picture with epilepsy, right, it's gonna be
It's
sort of
a-
overactive, sometimes even over-coordinated. They're all gonna be coordinated, where sometimes it's like, you guys like music? You guys like jazz? Right? Yeah. So some of the best, like, even when you're just having a jam session in jazz, let alone like an actual formal, say, orchestra of jazz or at a club or something, right? You're going to have times when you have volleys going back and forth in that music, right? You're going to have the saxophonist going back and forth with the drummer or what have you, right? Right? That's kind of the call and response model of jazz music. You guys follow any of that? Right? So part of what makes that music, if not any music, beautiful is there's times when it turns on and times when it turns off, right? You'll give and take with another musician in the band. You guys all follow what I'm talking about? Okay. So, right, in that case, it makes the signals, those musical signals, coordinated, and that coordination, that on and off, gives it kind of its acoustic beauty. So we like it, right? It's kind of like brain signals. They're going to go back and forth across different areas, across different networks. Signal, call, response, sort of back and forth. Oscillations, those rhythms, up and down. When you have something like epilepsy, it's when you give a bunch of 8-year-olds with no musical training access to all the instruments and they go, and they're all playing at once. Right? You're not going to have, you have an overactive, and it might be all coordinated at the same time, and you have the I'm not a musician, but so I don't even know all the who's in a jazz band, but you're gonna have the guitarist, the drummer, the flutist, the sax. Everybody might be playing the same notes at the same time. You don't have that delicate, elegant back and forth, on and off call and response, and that's why we see that in the trace. Does that kind of help?
Yeah.
Okay. All right, we feel pretty good about this question? Okay. And you wanted to know
It
about
was a neuron doctrine.
neuron doctrine. Yes, 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 yes,
Two
yes.
questions and then there were 2 answers that were.
Doctrine. Okay, so is it this one, the neuron doctrine? Was it A, confirmed using electron microscopy, B, proposed the existence of synaptic connections between neurons, 3, stem from the work of the great neuroanatomist Ramon Cajal, or D, all the above?
Oh, you know what? I got the one right actually. Never mind.
There could have been another one on the neuron doctrine. Was there another one you
No,
wanted to
that
look
was
for?
the one.
It was this one?
Yeah.
Okay, so, not everyone got every single question right, though, so, if anyone was curious about this one, it's definitely all of the above. So here's a trick, right, to getting the all of the above questions right. Huh? Well, one trick that I use, right, is you don't have to know that it's all of them, but if 2 of them are right, then it's gotta be all of the above. Yeah.
Honestly, yeah, that's the only reason I got that one right, because the electron microscopy, that kind of confused me
Yeah.
a little bit. I don't know, have we called it that before, or we just kind of always known it was the Golgi thing that he used, but that is what it is.
Yeah, really good question, Constance. So, if anybody didn't hear what Constance said, she said it was a little confusing, that she was able to get it right because she knew these 2 were right, even though she wasn't really quite sure about this one. Right? So we talked about electron, this is called microscopy. And so we didn't spend a whole lot of time emphasizing that. I may have mentioned it when we talked about those introductory parts of the class lectures, but it was definitely talked about in the text assigned readings, and it was talked about particularly in the context of this neuron doctrine, right, in this terms of the historical arc. So the idea is, right, you had the Golgi and Cajal sort of argument back and forth, the reticular formation, the single neuron sort of doctrine idea, individual discrete units, and it later, after their time, right, this neuron doctrine was confirmed using methods of electron microscopy, which is a super huge high power microscope that was able to go in and actually see the synaptic gap between 2 cells, which is just the method that was used to sort of like prove that to be the case. They talked about it a little bit in the text with that. We looked at some of those electron micrograph pictures. In fact, they were shaded, I think, yellow and blue in the different neurons, and you could see the little black synapse in between. So yeah. So that's where that came from. Definitely came from the text, and I probably referred to it a little bit in class. But you're right. The strategy, if you can get one or two, if you can't rule out 2 of them, then it's a pretty good bet that you can jump on that one. Yeah. All right. Good thinking. Any other questions on questions? Stuff that could have been wrong. I mean, it happens every now and then. We sneak a couple ones in on accident that might not make sense or that are badly worded on accident. So we fix those pretty easily. So if you guys see that stuff, you should definitely be looking back on your tests after you take them. And yeah.
I didn't get the chance to do that. So can I come to you and look at which ones that I missed? Or
Yes, you can, but you don't need to come to me. I believe you can see them on Blackboard.
Oh, you can still see it?
Yeah. So that's there on purpose because I want you guys to be able to use that as a resource and learn from it. And I just assumed, I mean, everybody, when I was in school, after you took a test, if you had it like this, you would just go back and look at all the ones you got wrong and figure, I just assumed that was happening. But it's there for that to be accessed. So that, I just always assumed that people would be going through those with a fine-tooth comb to find out how I was wrong. I mean, it's your point, so.
I tried, I couldn't find it. But
Yeah. So you might have to basically go to the exam and like, usually if you right-click over it, or there's a little like down arrow, it'll bring up a little menu, kind of like, let's see here. So let's say here you're at exam 1, see here this on the bottom? See how you can hit that down arrow, you can bring up stuff? Now this is my view, which might be different than your view, but it's probably something like that as a thing for you. Yeah.
You click on it, and then you want to click on the score, and then it grades it to the question.
Oh, okay, yeah. So it's something in your grade area. Hit the little down arrow, or the
You would click on the exam, and then it
Yeah.
shows you the score. You click on it, it shows you.
yeah. So it's pretty easy once you kind of fiddle with it a little bit. You'll figure it out. So okay, so that was good. We can review any other questions or stuff like that that you have from it as they come up. For the most part, it's a pretty standard test. We got a pretty standard bell curve. People did kind of normal. You know, some people did good, some people did bad, some people, for the most part, kind of came down in the middle. So it was about your standard bell curve, which means congratulations, we don't need to curve anything. We've already created the curve. So it's about normal. Now, did you have a question?
Yeah.
Yeah.
Something sparked in me right when I saw Lindsay come in.
All right.
She's not waving. So possibly would be like a better thing to do, to make sure that everybody turns in their stuff and it's not turned afterwards. If like Lindsay stays on one side of the room and everybody has to show her that it's been submitted.
That's a good idea.
That way we don't have to get penalized with the back and forth thing. You know?
Well, yeah, so I'll probably do both. And it's a good idea.
I like the scrolling thing.
Yeah, yeah, I like a lot of that stuff too. But when my goodwill gets taken advantage of, we have to also put a little of these micro steps in place. So it's a really good idea. We'll probably do a little bit of both.
Can we keep going back to the questions though? Because I definitely got
helps.
some right by going back and re-looking at them.
Yeah.
Maybe, we'll see. We'll see how it shakes out. Although it is good practice because that is how the GRE will be. It is how the MCAT will be. And
You could go back to the questions on the GRE.
maybe we'll set it up like that. Yeah. It's not gonna penalize anyone anything. Still the basic information. So, you know, this is a pretty good system, but you know, when people take advantage of it, it just kind of tightens up just a little bit to make sure that everyone can keep enjoying the benefits of the rest of the good system. Yeah.
How many people submitted after?
Oh, I don't know, a handful. Yeah, so I just got to do my part and just check into it. So we'll be doing that. Anywho, so we got that stuff. Any other thoughts or experiences on the test? It's definitely the easiest one we'll ever take in the class. So that's the good news, is that you got that one out from under your belt. Now we'll start the actual hard stuff and a little bit less review, but we're gonna make the hard stuff pretty accessible, pretty manageable. And you guys are gonna rise to the occasion because you have it in you, and I know you can do it. Everyone tends to always find a way to make that happen. So, okay. Let's see here. How many people want a chance to get some extra credit? Anybody not want to do more efforts to bump up their grades? Okay. Well, so I had an idea. You guys can veto it if you want. But I was thinking about ways to help you guys improve your scores. And particularly to help you improve your scores by also not just improving this test score, but hopefully improve your future test scores too. So I got a little creative and I came up with an idea. We don't have to do it if you don't want to, but I want to throw it out there, see what you think. You can pick it up and throw it in the trash, or you can throw it right back and we can work it out. But the idea is that I want to let you guys earn back some points on the test. That is, if you want. Sound like a good idea?
Yes.
So the idea is that because we can access these tests, right? You guys like the Tom Cruise movies, Mission Impossible? kind of phrase it like that. So, your mission, should you choose to accept it. Okay, will be to go access that test. And you will be able to earn points back on the questions that you got wrong. And here's how it'll work. So, it's going to take some work. Because ain't nothing free in life. But the work is going to hopefully help kind of see where some missteps might have been taken so that we can prevent the missteps in the future. So the idea is this. So for every question that you got wrong, in handwriting, write out what that question is. First, so you're going to have to do a couple things for each of these items you get wrong. So for every one you got wrong, write it out in hand, and write out the page number or the timestamp on the YouTube video of the lecture where that information was covered. So like the conversation we were having a minute ago, like was, goodness, we were talking about microscopy. So was that covered? I don't know. Yeah, I mean we forget certain stuff. So go back in the lectures and find out where in the timestamp did that happen. Write out that timestamp with the link. I mean you can paste the link or just say what lecture name it was and have to be the funky actual website link, but say what's the video name and what timestamp it was at 13 minutes and 46 seconds, or the page number, right? Which might be easier, but you know, either way, say here's where it happened, because I want to be able to foster this idea so that people really kind of can see that everything being tested is coming directly from the lecture and supplemented from the text. So sometimes there's misconceptions about that. So people think that we're testing stuff that wasn't covered in class, but everything was covered in class or it was referred to in the assignment. So for every question you get wrong, write out the page number or the timestamp when it happened. And then for every one of those wrong answers, write out why the correct answer happened to be correct. Kind of like we just kind of verbally went through about the EEG or epilepsy or something. Just write, here's why it was right, and also state why did the answer you happen to put, why was it wrong? And it might have been the case that it was wrong because maybe you hit the wrong button or maybe you just forgot. But like, indulge me a little bit. Don't be like, I hit the wrong button. Don't write, I forgot, or I was confused. Just say, you know, be academic about it and say, okay, so neurons don't move in the brain and the EEG is actually when it fires. You know, do that kind of thing. You know what I'm saying? So, yeah.
So a lot of questions I got wrong were the dendrites and axons, and I know the difference between the two, but my brain just like, whoop, you know,
Yeah.
Is that a valid answer for that kind of thing?
No, that's what I was talking about. Just indulge me with the assignment, like, right? Because then everyone can blow it off. They can be like, I knew it, I just, like that, and then it's not a helpful exercise. And then you're wasting your time to just get points.
So you want me to make something up?
No, I want you to actually say what the truth is about dendrites and axons in the context of that question.
No, I know, but why did I put it wrong?
No, why is that particular option happen to be wrong?
Okay.
Kind of like we did a minute ago about why the answer about the neurons moving was the wrong answer. That's all. Yeah, I mean, just be fair, because I'm trying to hook you guys up with a fantastic opportunity. You know, and again, like, people are going to take advantage of it and kind of like shitbag it, for lack of a better word, then, I mean, I'm just going to drop it like it's hot and we're just going to keep everyone's scores. Yeah.
How many points do we get for the ones?
That is a good question. I will get there in just a moment. I'm only halfway through the task. Yes?
Did you say that we have to like print it all out or can we type it?
No, handwritten.
Okay.
Yeah. Okay, so permit me, if you will, to continue. So there will also be some additional questions that were not tested that I will post on Blackboard. And we'll do the same task. And just say why the right answer is right, why the wrong answer is wrong. Or just, in this case, why is the right answer right? I'll put 5 or somewhere between 5 or 10 more, and they will be taken directly from some of the quiz questions that are for free available, provided by your textbook online. So a little bit of a nudge here to get you guys to remember, oh yeah, that resource is available online. And so you can see where it's at, you can practice using it, and hopefully use that as a resource for the future. Question there and then there.
I have a question for after that explains.
Yes.
Where do you find like the quiz textbook questions?
It's a great question. I believe there's a link in the syllabus.
Because I tried clicking the link and you had to put in like a password and stuff.
Uh-oh.
Because it was what was provided, I didn't.
Oh, you might need a password of the actual text or something, yeah.
There's an activation code, so like if you, I don't know how, if you already have the book, you would buy an activation code, but there's like an activation code to like link to the class.
Yes,
So
that is there's an activation code usually in the inside cover of the book, yes.
So you can either purchase it. I bought my book used, so unfortunately someone already used the code, so you can't use it twice. So if you guys really want access to it, you can just purchase it. Because if you go to the website, it's behavioral neuroscience and then he.com. It allows you to purchase it if you want to purchase it. So if you really do want access, or you guys could like, people can get together, chip in, and then you guys could all just get access to it.
Yes, sir.
Could they offer that 2-week trial where you can just download everything?
No trial. Yeah, it's either purchase or purchase.
Yes?
And that's basically what I was gonna say, but I tried to do that and it didn't happen.
Okay, so that's really helpful for me to learn because I don't work on that side of the equation. So it sounds like that is the answer. It is accessible. It might not be accessible for free. You won't need it, which is why I encourage you to do it. I mean, what's a small investment of a few dollars to help practice? It might be not that much of an investment considering how much you're probably taking out for loans or paying in tuition. But regardless of that recommendation to invest in yourself, because you are the best investment you will ever make, I'll be posting those quiz questions on Blackboard for you so that you don't have to do that for this assignment should you choose to accept the mission. Okay, so we will do that. And then the last part of the mission assignment will be to write out, in handwriting, a little bit of a self-reflection exercise, which is to just write down and log your estimated hours spent each of the weeks preparing for that first exam. So how many hours per week do you think you spent preparing? And then spend a few moments sort of maturely self-reflecting and write out a short statement of that self-reflection and analysis of what your study plan is now for improving your score in the next exam. So I want to sort of foster that good sort of debriefing attitude and ability to kind of self-reflect, critically analyze, and see where might you want to re-tailor, maybe in a big shift or maybe a little micro-tailoring a little bit, to see where we can retarget to make sure that we can get on the right track if you need it. So, not always the easiest thing to do in being honest with ourselves, but it's also not a 20-page essay assignment, which I think means that it's kind of an easy thing to do. So those will be the 4 criteria, which, by the way, I'll have posted on Blackboard, so if you didn't write it down, you can always go back to the video and slow it down of exactly what was said. Or speed it up and listen to exactly what I just said, which is exactly what I read off of here, which is also exactly what's going to be, and already is on Blackboard. I just need to make it accessible for you. So, those 4 things are, write out for every answer the page number or the timestamp of where that information was provided. And then for all the wrong answers, write out why the correct answer was right, why the wrong answer was wrong, and do that for another additional questions that will be posted probably by the end of the day on Blackboard, together with that sort of self-reflection of what the hours that you estimated that you put in this time around, and then what is sort of a self-analysis of what might be some targets of some ideas that you might want to do to really do good in the next one. And a couple of hints on this, right, is to do what we're doing now, but do this for the next one before the test, right? These are good ways to study, right? So get together with the study group. go to the SI sessions. Do the things that are going to help practice work with the material, because the material's tough, but it's tough at first. When you practice, when you use it every day, you're going to surprise yourself at how fluent you get with it. But mostly by virtue of being corrected by your friends and peers in conversation and study groups. Yes, ma'am.
And then, would you like this due on Wednesday?
That's a good question. Let me finish the last part. I'll come back to that. Got to think of an answer first. But if you do that, and if it's all of those things are done in completion, you'll get half credit back for every lost point, or for every wrong answer, you'll earn back half. Which, if you find a better deal this side of the Mississippi, I dare you to. I don't think it exists. Yes.
Do we have to do the extra blackboard questions?
Yes, it's part of the deal. So, if you don't want to do more work after the test, the message is to do more work before the test. It prevents doing the extra work afterwards.
How many extra questions are
I haven't decided yet. Somewhere between 5 and 10. Or you don't have to do it all. If you're happy with what you got, roll with it. And it will be due, that's a good question. What's it, Monday today?
Yeah.
All day? I don't know, you want to say turned into class at the beginning of class on Wednesday? No. Turned in tomorrow instead? That's it. That's the option. Tomorrow or Wednesday. Okay. The reason I say that is because what I don't want to happen is I don't want this. So first of all, you shouldn't get dragged down for the next section's studying. You need to get this done and get it out of the way. And so we need to move ahead. We need to move on. It's time to start. You gotta spend this time on the other upcoming stuff. And so the faster it is, it is. So you can do it tomorrow if you want, but I suppose I won't make friends like that. But hopefully you guys can appreciate the generosity of the opportunity for Wednesday. Sound reasonable? Or just don't do it too. I mean, you don't have to. It's completely a freebie. You know? Are there questions? Okay, I will make that available right now. Down here. Edit. And we will make that available. Sound pretty good? Okay, so if you have any questions on how to do it, it's right there on Blackboard, right at the bottom there. Exam earn back instructions, exam 1. Sound good? All right. My recommendation is to take what you learn, not just the information, but take what you learn about, maybe how did I miss this stuff the first time around? Right? Or how did I not read this in the right way, or it slipped my mind? Or whatever, you know, I confused axons and dendrites or something. How did the book put this in a way that was then basically asked about it directly in the test that I can now fix up so not to miss it again the next time? Yeah.
Can we also draw diagrams?
You can if it helps you to explain your point.
Okay.
That's why I like it in handwriting as opposed to digitally. Plus handwriting is slower, so it gives you more time to think about it while you're doing it, so it gets dialed into our noodles a little bit tighter. And then hopefully we can take the same strategy, maybe help to do that on the readings for the upcoming stuff. Sound like a good deal? All right, cool. So, all right. So we'll talk a little bit about the visual system today. Let's see here. Let's dive right in. So how many of you guys have studied the visual system before in other classes? About half of you? Okay. So for some of you guys, it's going to start off as a little review, and then we're going to build on that and add some new stuff. Or maybe it'll seem new if you forgot it. For you guys who haven't, had it yet. It'll be kind of an introduction, and we'll see how it is that we interact with the world, right? So imagine you're blind, and you gotta walk around, you gotta figure out what's in this world, right? And then you open your eyes, and now you get all this light coming in, right? So the first thing it tells us is that light is the physical stimulus of the visual system, and we're gonna look at that and break it down to even getting into kind of the questions of physics, like what is light? Well, it's photons, little particles, photons, and they kind of oscillate at a certain wavelength or frequency, and we'll start to see how this even gives us our ability to perceive things like color, shapes, edges, and how the cognitive systems in our visual system can then construct that information together independently. That is, independent information of color, shapes, edges, and weave that together into our rich experience of what we see. It's pretty remarkable. We still don't even understand it all yet, of how that works, which is amazing. Because what we see, those beautiful colors, Ryan Gosling's eyes when he says, "Hey girl," right? That perception is just based on ions moving in and out of protein channels, which is crazy that he can be that beautiful, right? Okay, so we're going to look at kind of how that happens. So we're, let's see here. The ideas that we'll talk about are that this system is going to extend from the eye to the brain, and they're going to travel through these different cells. We asked about a couple of them in the retinal ganglion cells, the horizontal cells, the amacrine cells. This network of a retinal system, then progressing to different areas in the brain, and that there can be different layers or levels of that that can characterize and serve very different types of what we'll call receptive fields. So this idea of a receptive field is something that will be consistent through the next several weeks of our class. We'll see it in the auditory system, we'll see it in the somatosensory system, we'll see it in the visual system, and just about every other thing, which is this idea that there's a part of our environment that a cell can detect stuff in, action in. And there's another part that it can't. So the stuff that, the part of our visual field that a single cell can detect activity in is the area that it's receptive to. So that's the field, the receptive field. So kind of like, I don't know, let's just imagine that you're some sneaky, nefarious student and you're cheating right now, right? And you've got this evil professor who you don't want to catch you cheating, and I don't know, whatever, right? Or mom, you don't want mom to catch you, I don't know, sneaking a cookie from the cookie jar, right? And you know the idea of a receptive field right now, because that's the area that I can see you in. So if I'm over here talking to Rosie, Roman knows he can get away with it because I don't have eyes on the side of my head, because he knows that he's outside of my receptive field, and vice versa. Right? If I'm over here, you know that I can't see you. So I don't know, you might be Snapchatting or doing something that you shouldn't be doing in class. I don't know. You guys get the idea. That's the receptive field. And so we'll talk about that through almost the entire duration of the rest of the quarter for these different sensory modalities. We'll also get to the idea that there's columnar organization. So even within an area of cortex, you have a column, and there can be different layers in that column that can process information in different ways. And we'll see particularly that you can have several different streams of information processing across columns too. So for those of you guys who might have had visual lectures before, or lectures on the visual system, you might remember the dorsal and ventral streams, for example. These sort of streams of information processing across columns. If we have time, hopefully we'll be able to look at some deficits in the visual system too, and kind of how that reflects some of the properties and principles that we'll be talking about. So the basic idea when we look at the visual system is that we're first going to just start with this basic model of the eyeball. So now we're looking kind of down from a bird's eye view, and you're going to have our main information of light coming in, right? And so light is what lets us see that, in this case, that R. Now, what we see ends up getting inverted. This is why we see it upside down here on the back of our eyeball. We call it retina. So this information comes in, it hits this lens here, and the lens inverts it and refracts it on the back of our eyeball. Now in the back of our eyeball is we have this area called the retina, and we're going to dive and take a deep dive right into here. We're going to find that there's like a gajillion different cells doing some pretty funky and remarkable stuff. Okay? Some other things that are happening, right? We innervate the eyeball with nutrients and oxygen that keeps these cells alive. That happens by blood. And so we have some blood vessels in the eye. We have these muscles on the side. Okay? We have these ciliary muscles that can, if you pull them this way, it's going to flatten out our lens, right? If you relax these muscles, it's going to allow it to push in, and that lens gets a little fatter. You guys see how that can happen? It's kind of what's happening when you're squinting. You guys ever have to squint to see something a little bit more detail? Right? Squeeze those muscles a little tighter. You're going to pinch this a little bit and focus that a little bit more on the central point of fixation in your retina. Okay? What you might call the fovea. Okay? This sort of central part. You're also going to have, let's see here. You have your iris. Okay, this part over here. It's going to come in and make that sort of black area around your pupil. This, of course, is that pupil, that opening into the middle of your eye. And all this light, these photons of light we'll look at, it's going to get projected and detected by photoreceptors. Photoreceptors detect photons of light. Okay? Which is really remarkable because it's one of the only parts of our visual system that can be accessed essentially outside the skull. Right? So when I look any of you guys in the eye, or you look your star-crossed lovers in the eye, right? You have that eye connection. So your neurons are firing with access to the other person's neurons. Most of our other neurons are locked up within the skull or the spinal cord. You know, that they're encapsulated in something. You know? If we hold hands, our neurons are connecting. It's our skin. Right? You have a direct connection from the photon to the nervous system, which is pretty cool. And we'll see that information is going to get sent out through this optic disc and sent back into the brain. And we'll take a look at those next steps of processing too. We spend a lot of time though digging into what's happening here. What do we call it? Transduction of this signal. How do we transduce something that's a physical stimulus like a photon of light into an electrical stimulus like a graded potential or an actual potential to send that signal deep into the brain and then to somehow give that meaning to where it means something to us, right? And how do you tell the difference between the pattern of photons that are coming in and hitting your eye that looks like, I don't know, let's stick with your Ryan Gosling example. Mine. Yeah, well, the example I gave to you, the example you were all operating with for my example, but, and how does that perception differentiate that photon or two or millions of photons of light that you're seeing from Ryan Gosling from that you might see of the other example I use all the time in Drake? Pretty different. How do we make sense of that? They're all just little action potentials or graded potentials changing some glutamate being exchanged across cells. Pretty remarkable. So let's take a dive and kind of see. So those are kind of the visual representation. If we come back, I'm just showing you on the slides. These are two of the slides we skipped over, but it just talks about those same vocabulary terms that we just covered. Okay. Okay. Let's see here. Okay, so let's talk about some of these things. So when we look at these retinas, okay, we're going to look at a little chunk we're gonna zoom in on this retina. We're gonna see all sorts of layers of cells in there. It's gonna include ganglion cells, bipolar cells, rods, cones. Ooh, by the way, anybody know the difference between rods and cones? Yes.
Rods are for color and cones are for black and white, and then, there are less rods than there are cones.
Can you say that again, please?
There
I see
are,
that. There are more rods.
so I was gonna say, yeah, there are more.
Okay, well, okay, so this is really good. So we got somebody saying there's more rods than there are
It's
cones.
about 100 million, I think it is, versus like a full 5
There's-
million.
Yeah, but where are there more rods versus more cones? It's kind of a relative question, right?
Rods are on the outside, if I remember correctly.
Yeah.
Cones are the
Yeah, so
More
they're
centered
concentrated
body.
differentially is the idea. Yeah, absolutely. And we'll look at how they're concentrated differentially, where the rods are on the periphery, the outside, and the cones are more towards the center. Now, what were you saying about cone?
There, I'm, never mind.
No, it's okay, it's okay, it's okay. Come on. It's good, it's good.
Okay, so rods are for color, and then cones are for black and white. Am I, is that totally wrong? Is that backwards?
That's what I said. What were you saying again? Do you want to rephrase that?
No, I'm okay.
No, please, rephrase it. Please do, actually. No, it's okay. Just say the
I have
opposite.
performance anxiety, and I'm getting it right now.
No, just say the opposite.
Okay, there, you know what's so sad that I wrote it down too?
No, this is not sad at all. This is a great victory.
It's written down incorrectly, okay. So
No, this is exactly what we're trying to do. We're trying to fix up some of these little tweaks. Yeah.
Okay,
That was
so,
good.
so rods are for color, I mean for black and white, and then the cones are for color.
Yeah. So the cones are gonna help detect sensitivity to colors, and the rods are gonna help detect black and white. Don't feel bad. Dude, I looked terrible this weekend. So I looked like a deer in the headlights. So I know how you feel. So I got to accept an award at UC Davis. They had like a big alumni awards this week on Friday. I had to drive up to Davis for like 6 or 7 hours, and then get all dressed up in a monkey suit and yeah, not like a tail and ears. You guys know they call tuxedos monkey suits, right? Okay.
You're disappointing us now.
Oh yeah, sorry. Maybe one day they'll combine the two kinds of monkey suits. But they all get dressed up in a tuxedo. It was a really big fancy thing. It was a really great honor. And they said in the email preparing us that they're going to call us on stage to give us our reward. And they said, you're not going to have to give a speech, so don't give a speech. We're just going to ask you a question like, what's a lesson that you learned from the UC Davis community or something, and then step off the stage. So I was like, all right, cool. No speech, didn't prepare anything. And I was like halfway in the list of people they were calling off for awards, and everyone's giving these speeches. I'm like, oh crap. And I was really scared, I was really nervous, and there's huge lights, spotlights, and so I got up there, and it was all, they had the big, put me on the screen and everything, and I was so terrified. And I just kind of had this deer in the headlights, and I gave the speech, I'm like, and I just had the answer to the question of, how they helped, what I learned about, from the community in Davis. I had a nice little short answer, keep it short, sweet. And I was like, crap, they want more, everyone's giving speeches. And so I had a horrible stage fright, and had these big, huge eyeballs in this picture. I looked like a huge dork. And really embarrassing, and I know how you feel.
There's tears.
Yeah, I felt those too. You guys know how I salvaged it? I redirected it really craftily. Indeed, to my wife. And so I talked about actually, how I learned, how no person is actually an island. You're out there, you're doing this work on your own, and parts of it you have to do, but really one of the things I learned from the community is how important the teamwork is to success in any big endeavor that you're pursuing. The faculty, staff, this and that, and I said, and I'm terrified, I'm literally holding the microphone with both hands, like this. Yeah, it was horrible. And they had sent me a picture where my eyes were full out deer in the headlights. And I said, but most importantly, if I took anything, the most important thing I took away from Davis was that or the best thing I actually got from Dave is sitting in the back of the room is that my lovely fiancée back there, she's in the one too. Everyone looked that way and I ran up. Yeah, it was terrifying, so don't worry. It's good practice. You'll accept an award one day and you'll be very, very comfortable with it.
Did she throw you under the bus too?
Yeah, that was later though. Once we went home, she, beat me with a stick or something. She's very shy, so she doesn't like being called out for those things. But she does great stuff too, so she deserves some of the spotlight. And it's true, we can't do the things we do without the
So
support
what
of
you
people
learned?
like her. I'm
It's
sorry?
better to be over-prepared than not prepared at all.
It is, yeah. And I had a lot. I'm sorry?
We should have just kept it short,
Oh, I did keep it short.
like super short.
It was the shortest speech there.
Good.
Yeah, that's what I said. I was actually, like, they said, don't give a speech. I'm like, all right. I had some stuff to say, but I kept it nice and tight and sweet. It was good, so. Yeah. And in fact, everybody else stole my lines then afterwards. Because then they all started talking about teamwork and their wives. Nobody mentioned their husbands or wives until then. And then they remembered. They couldn't not then after that. So, anyways. Okay, so, really good questions. Ask more. We need to, that's exactly what I want to do, is help fix some of that stuff up. And you're doing a great job.
I was so something.
No, that's okay though. That's okay. That's a good thing. It's a good thing. Okay, so let's take a closer look at some of these neural networks. Yeah. Yeah, don't sweat it. So, if it makes you feel better, I'll tell you another story.
Okay, you can keep going.
I once accidentally turned off the lights in a lecture in Princeton that I wasn't supposed to be in. And I was like probably 19 or 20-year-old kid sneaking into these lectures at Princeton. It was like Nobel Prize winners there. And Danny Kahneman, he won the Nobel Prize in 2000 in psychology. And they had just built a brand new lecture hall that I hadn't been in before, and I used to sneak into these classes because I'd go to the cheap state school down the road. And I came in late because I'd have to take the bus to the train station, to the train connection shuttle, and then walk across campus. It took forever to go 15 miles, but I didn't have a car, so I was taking all the public transportation. So I got there, it was about 5 minutes late. And I just snuck up against the wall to stay out of the way, right? So I didn't want to walk up in here and sit there in front of everybody. I was way too nervous. So I'm just sitting here watching the lecture. As they start talking, the lights go down, as lectures tend to do, and then it goes whoosh, pitch black. And everyone's like, lights, lights, and I'm thinking, yeah, he's the asshole who turned off the lights. Right? And I'm like, yeah, get this guy, get him out of here, turn. And then I realized it's one of these new smart classrooms where it's not like the light switch where it's sticking out, like normal people, but they're fancy Princetonites, and everything's flat, and it's what? And I'd been leaning up against it, and it was me who was the big dork who turned off the light. And I said, oh crap, crap, crap. And so it's nice, I hitting it. And it's, right, if you guys ever play with these light switches, they're on a delay. So you start hitting them and they don't respond. So I'm hitting them like crazy. And then it just whoosh. Now everyone's like, turn them off. And I was, mortified.
Did you leave?
I wanted to leave, but it would have made it worse. At that point, you got to just play it off like it wasn't you. You'd be like, oh, yeah, that was, somebody over there or something. And it was fine. It was a fun story to tell. So don't be intimidated for making mistakes. Those things happen all the time. And I promise you, I've made bigger ones that are way more embarrassing than anything like that. So when we talk about these ganglia cell networks, let's take a closer look. So if you remember, this is diving and pulling out from that retina, right? And we can see so we have our rods and our cones. Okay, so which ones do color and which ones do black and white? Cones are color. Yeah, really easy. C is C and C, color and cone. Okay? So the reason they call them cones is because they're shaped like a cone. The rods just look like a rod. Super easy there. We'll look into that in a little bit more detail. We're gonna see this black box here, we're gonna zoom out, or zoom in actually, we're gonna look at these in more depth. But first let's take a look at the bigger picture of what's happening here. So we're gonna have light, and light's actually, I always got confused by this, but it makes more sense now. Light's coming in this way. Okay? It's gonna pass through all of these that will not care about the light. The light is going to hit these outer segments of these photoreceptor cells. The only reason that these photoreceptor cells care about the light and these allow it to just pass through is because they have specialized proteins in them. We talked about in last class, the opsins. Remember? Optogenetics. Rhodopsin. Yeah, so these cells have those specialized proteins that almost magically will actually care about light and will change when light hits them. They're not in here. So the light passes right through here, hits these guys, institutes these crazy changes of events that we'll look at in much more detail, and then sends signals. First to these bipolar cells in purple. So see how you have the nucleus and there's bipolar, 1, 2 extensions coming out, okay? The bipolar cells, they're going to send a message then to these cells, which are the retinal ganglion cells. Okay? These retinal ganglion cells are going to send their axons out through here and it'll go up, yeah. What you got, Constance?
No, okay, I got it now.
Okay.
Yeah, you just like rocked my world when you told me that's where the light enters, because I was thinking it was the other way around.
Yeah, I always used to think the same thing too. Like it freaked me out. I was like, how? And it just didn't make sense. So one of the things that they actually made fun of me for on Friday at this talk is I had one of my professors from neuroscience when I was a student there. She had to give a little introduction and tell some stuff, and she said that when I was a student, she's like, I kind of drove her nuts a little bit, I bet. She didn't say I drove her nuts, but it's a nice way of saying someone drove you nuts without saying they drove you nuts. But she's like, he asked so many questions in class. It was like, it's probably that kid who doesn't shut up in class and keeps raising his hand and annoys everyone. But she's like, but you could tell, like, it made the learning happen. And you could tell how curious and insatiable that drive is to learn. Because I thought it was the other way. And so I had to keep asking questions. And I'm like, how? But the light is coming, and I was so confused. And then once it happened, and it clicked, and then you're like, okay, yeah, that makes sense. So the light's going to pass through here, and then it's signal. So that's the light that comes this way. But it's the electrical signals that come this way and then out. And I'm going to back this slide up 2 slides, and we're going to look back again, or 1 slide. So remember, we're talking about the light coming in this way. The light's going to hit here. It's going to go through here, hit the photoreceptor cells, and then come back this way. The electrical signal is then going to get sent here, and then come out here.
Can you go back to the other one?
Yeah. So, but I want you to remember this look, okay? Because we're going to look right in here.
So that's all part of the optic nerve.
This is the optic nerve here.
What is this? That?
These are the axons from the ganglion cells,
Okay.
and they feed out and become the optic nerve.
Okay.
Wait, I'm sorry. So, okay, the light comes in through there, hits the photoreceptors, and then where does it go after?
The light doesn't go anywhere else. The electrical signal. So the light comes this way. The electrical signal then goes whoop, whoop, whoop. Okay, so keep that little zoomed in box because we're going to go right back into here now. This is the same zoomed in box. And the light's coming here. The electrical signal is going to come here, and then out through the optic nerve. Is that helpful? Because that always confused the ever-living heck out of me for like years. Yes?
So, essentially light passes through all that stuff and then it gets transferred into electrical signal back out.
Yes, absolutely. Totally. Yeah, I mean, it's tricky.
Then how come, never mind, that makes sense then.
Yeah.
Well, I was gonna say, how come the graded potentials happen at the bipolar, but because they make up the optic nerve, that makes sense.
Yeah.
So when we'll get to this, that's really good foreshadowing. We'll talk about gradient potentials. So action potentials don't happen here. Action potentials don't happen here. But they do happen here at this axon hillock and sends the action potentials out. Because these are really the players that are going to send that signal into the brain, right? These are kind of your feelers out there detecting stuff, right? So you're feeling around for those light particles, and then when you get enough of those light particles that you feel and you grab, and they all come together at the same time in a big enough signal, then you'll have an action potential get sent out. Make sense?
So how does that work for rods then?
The same way.
Well, even when there's no light coming in, or
There is. It's just lower luminance. Luminance, we need brightness. So it's not as bright, the colors. But you can still see some light. Now, if you're in pitch black, you're in pitch black. You don't see anything, right? Try waking up in the middle of the night to go pee, right? You're just going to stumble into everything and make a big mess. You need a little bit of the light on. Yes, Constance?
So then, rod cells are more sensitive to low light.
Yes.
Is that because color is just brighter in general, or?
Well, it's because colors are brighter in general, and because the actual opsons in them are sensitive to different wavelengths and frequencies of the different photons. And we're going to get into the color spectrum in a little bit, and we'll see that. Yes, and then we got to move on to the next part.
Yes, sorry. Are opsins the proteins?
Yeah. 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 Okay, so let's take some closer looks here. Okay, now we're zooming in into our photoreceptors. Okay, we talked about there's two kinds, a rod and a cone. They're basically operating very similar. The big difference, again, is this protein machinery, and which one it's kind of, sometimes, maybe the book does this too, sometimes people present the auditory system first about how we hear stuff. Right, so there's a different tone, right? You can have a bass, you can have a treble, right? Different sounds, different pitches, right? You can be like Meghan Trainor and be all about that bass, but no treble, right? Or vice versa, okay? Those are different frequencies of sound. And we know that because we hear it differently, right? The same is true for different frequencies of our light that we experience as colors, or black and white, or different colors. So that's kind of your question, Roman. The frequencies of those photons, the wavelength as they're called, is like the equivalent of a treble versus bass. And different cells are specialized to detect different levels of that. Yeah. And so, but other than that, they're going to work real similar. They're going to have a section that we call the outer segment. They're going to have an inner segment, and they're going to have the nucleus, and then they're going to have its axon out there. So these are kind of like the dendrites. And we're going to look into here, and these are called discs. We're going to take a snapshot. We might even look three-dimensionally into these discs, and we'll look at some of the molecular machinery that's in there. Okay? Now this is this top part. Can you guys see my pointer? Yeah? So here we can see that top part, this axon. But we can see that it's got all these little black dots that we're going to call neurotransmitters. It's glutamate. Big thing to know. Visual system works through glutamatergic transmission. Glutamate, glutamate, glutamate. Okay? So glutamate is being released. Now here's the crazy thing. We'll come back and talk about these topics as we're kind of keep revisiting it. But it's always confusing when we start learning about this. Because we always finish just talking about action potentials, right? And it's kind of like the cell is always quiet, quiet, quiet. And then an action potential happens in response to an event. This is kind of the opposite. In our photoreceptive cells, they are constantly releasing glutamate when it's dark. When the light comes on, it actually turns the glutamate off. Okay, we're going to come back and revisit that idea. But I want to throw that out there. And it will make sense, yeah. Like there's actually some pretty nifty strategies to it. For example, how many of you guys have kids? Anybody? A
How many of you guys have kids?
Does my dog count?
Your dog, it depends. Is it a spoiled princess like Juno?
No.
You don't think she's a kid. How many of you guys have been a kid? Everybody, right? You ever been yelled at your parents for not checking in at some point? And as a teenager being left out at night or something? Right? Okay. Why do they want you to check in? Because they probably care about you, they love you, they want to make sure you're not dead, right? Okay, cool. That's kind of a good thing most of the time. So they want you to do that because what they don't want is there to be silence and you only call when there's an emergency or if you need money, which might be an emergency, right? What we want is your mom, I know my mom, I just saw her this weekend. She got to come watch me be a deer in a headlight. She likes to know that I'm okay. Sometimes annoyingly so. Check in with me, is everything all right? Let me know you got I'm okay. Okay, I always forget. They want to know that you send those text messages. When things are normal, just send me your text messages every hour, just check in. Right, curfew's at midnight. Okay, check in every hour. That way they know if they don't hear from you, it's not that things are quiet and you learn that an event happened by something occurring. It's that there's regular activity. Every now and then there's a random text. You want to make sure your boo or your bae says, oh hey, what's up? Because it's when it goes quiet, when they ghost you, that you think, that you can tell something's wrong. So it's the absence. It's when that information goes down, the signaling goes down, that we get real discriminability of what might be happening in our world. And that's what we'll talk about with this glutamate transmission. So the glutamate's kind of always being released in a constant flow in the dark. Kind of like you want your girl or your guy to be sending you regular text. Just saying hi, just knowing everything's okay, because we're all insecure and we just want to know everything's okay, right? Yeah, I used to get yelled at for that because I wouldn't do that very well. So Erica got mad at me. It's like, how come you never text me? I'm like, what do you want me to say? She's like, I don't know. Like, hi? I said hi. Tell me, I don't know what's going on. I'm like, I'm working with him. I have nothing to say. Don't say that, guys. But, you like to know that everything's okay. So we'll take a look at some of those elements. So this is those outer segment discs. And this is kind of that three-dimensional look. God bless you. And we're going to look at some slides where there's this model. Okay, this is a three-dimensional slice through here. So we've cut out like a corner of this. Okay? And we're going to look at how some molecular activities here allow us to detect light. Okay? Okay, we're also going to see some of those lateral cells, or lateral inhibition, these horizontal and amacrine cells, okay? And we're going to talk about this idea that all of our cell types are going to generate graded potentials. Just like we introduced a few minutes ago, the only place action potentials are happening are in the retinal ganglion cells, right? They're the ones actually sending information. So you guys remember we talked about this army analogy last class with convergence and divergence, right? So the photoreceptor cells, the bipolar cells, they're kind of like the privates out in the field, right? They're kind of like the enlisted guys. They're out there, boots on the ground, collecting intel, collecting information, and they're feeding this back to the generals. But to get to the generals, it's got to go through their officer, right? The person in charge, and that person has to decide, bam, we're sending a signal up the chain of command. That's our action potentials from the ganglion cells. We're getting graded potentials from the guys out in the field, kind of seeing how things are going. Okay, and we'll kind of come back to this idea as we move along. Okay, now when you see these words photopic and scotopic, they're going to seem a little crazy, but it's really easy. Okay, photopic means color because you're drawing on the cones. So photos, let's just think of color photos, right? Photopic systems are allowing color, and that's going to be the cones. These are just fancy words that you'll read about, and so don't let them confuse you, throw you off your game. Scotopic sounds really crazy. That's kind of a weird word, but that just means black and white. It just means the rods. Okay, so okay. Now this is just a table from your text. But the idea is that it's contrasting the rods here and the cones here. okay? And what you should be able to do, if you want a good little study tip, is just rewrite this table. You'll learn the difference between the rods and the cones. I used to just give people a blank slide with a table in it. It's just crisscrossing lines. And I said, here, just fill in the table. But you guys, it turns out, college kids are pretty good at making lines, and you guys can make those tables on your own. So make a little table, crisscross them, and just go column here, and column here. And so you have essentially cones, rods. You're going to compare how many of them are there. There's about 4 million cones, but there's a ton more rods. You're going to want to know, are they concentrated in what part of the retina? On the sides, like Roman was saying earlier, or called the periphery, or in the middle, right? The middle, there's a lot of color responsive cells, those cones. The rods are on the side. A little trick that sailors discovered thousands of years ago. You guys ever sail? You guys ever been out? You sailed? You ever sail at night? Okay, so what sailors would do at night is they'd have to use celestial navigation. They'd have to use the stars to navigate. But it's dark. The stars are just tiny little pinpricks of light, right? Okay. So when you look directly at that star at night, that light in very low luminance, luminance means brightness, so we have sensitivity to luminance, okay? High sensitivity to luminance, meaning that it can be stimulated by a weak light. Okay, so the reason that our rods are good for night vision is their little proteins for that wavelength, frequency of light, is very, 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 very sensitive. So you can use them for like night vision. So when sailors need to see these stars at night, they wouldn't look straight at the stars because that light would go straight to the back of their retina where there are not rods. So what they would do is they'd look off to the side. They'd look in their periphery so that light would come into the side. Now this is before they even invented microscopes. They didn't know why they were doing this. They just knew it worked. Pretty cool, right? Yeah. Okay. So let's see here. So we talk about some basic physics here, okay? And this is kind of what we've been getting at. This idea that you have this wavelength of light, and you can break down these photons into this sort of unit called a quantum, okay? So that's kind of like the physical stimuli of this light within this sort of electromagnetic band. We look at that in these kind of wavelengths, which is really just a reference to sort of frequency, super high frequency. And these quantum lights are going to be visible. Most of them are not visible. We have a very, very small, limited band of these quanta that are in the visible frequency of light. We call those photons, like we've been talking about. So this is showing this tiny little bitty baby part of the electromagnetic spectrum that our eyes can see. Basically, we can't see jack. Look at how much else is happening in our electromagnetic spectrum. And we can't see it. All we can see, so right, this is zooming in on our rainbow. So this is our color spectrum. It's our rainbow. Okay? Now, these colors just simply represent these photons at certain wavelengths, or nanometers. NM means nanometers. Okay? And so it goes 400 to 700 nanometers, which is really pretty small when you look at the range that they could be in. So, just a little context. We're really just talking about a tiny little baby window, but it provides the basis for everything we see, do, and live. Right? Which is pretty cool. So you'll see different cone cells will be preferentially selective to detecting different numbers of these wavelengths. So if you have a cone cell that likes a wavelength of 650 nanometers, what color cone cell would you label it as? Yeah. And it's going to have a little bit of a bell curve. It'll drop And so it might pick up a little bit of this, but it's really gonna like its maximal sensitivity would be over here, which is what we experience and perceive as red. And vice versa for these other ones, okay? So, as we talked about with our last lecture, we have these things called opsins, these proteins, right? So it's part of these photopigments, particularly something called rhodopsin, okay? So that's particularly useful for detecting color, okay? And the idea is that it's going to contain two things. One, this thing called retinol, which is a chemical, and this thing called an opsin, okay? And so we're going to see that when light is going to hit this thing called rhodopsin, okay, this photopigment, that the part that we're going to call retinol, this chemical, okay, it's going to dissociate, which means it's going to separate, okay? And it's going to activate this other thing called an opsin. Now that just sounds like a bunch of wonky words. It's a lot easier to see in a picture, okay? And so that's kind of what we're going to start looking at here, okay? So when we're looking at this cell, this rod cell, we're measuring its electrical potential, okay? So this is an amplifier. We got a little needle in here. We're measuring its electrical potential. And it's basically depolarized. It's not like what you're used to in action potentials. It's got a very close to zero membrane potential, which is why it's releasing all that glutamate in the dark. So it's just hanging out, chillaxing, shooting some pool, maybe even shooting some b-ball outside the school. You know, you don't even want to know what's going to happen when a couple of guys who are up to no good start making trouble in your neighborhood. Okay, so it's just hanging out in the dark. We're going to look in one of these discs. We're going to see that there's these proteins, or these channels, well, the channels of proteins. And that's going to be where our photopigments are. And these rhodopsins. Okay, and here's where we go. Here's that disc that we've been talking about. We're zoomed super in. Here is our channel, okay? Now we're going to see, light is going to hit this. This is that retinol chemical that I talked about, right? That little, looks like a little chemical shape, right? We're not like into organic chemistry here, so don't sweat the details of that. Okay? All you got to know is it's this squiggly little shape. It's retinol. When light hits it, these quantums of light, these photons come in, it's almost like magic. Right? Except it's science instead. And it's going to hit this, and it's going to induce what's called a conformational change in this protein, which means it's going to rotate and get weird. It's going to change. Right? It's going to get its butt kicked into gear. Light's going to hit this, okay? And it's going to start to dissociate, which means things are going to fall apart and change off of it. Now, it's actually going to induce these parts of this protein to come apart, and it's going to move over here and induce some changes, okay? So there's this thing here called transducin. It's now going to be activated, okay? So by this inducing this conformational change, it's going to activate transducin. Transducin is then going to dissociate, okay? And thanks to GTP, it's going to get added to transducin. It's going to dissociate, and the transducin is going to move away from this channel. It's going to move over here, okay? Because this thing called GTP, you don't even have to know what it stands for, and trust me, you don't want to know what it stands for. Crazy long word. You'll thank me later. Okay? Nice and easy. Okay? GDP is going to be added. It's going to dissociate. By it, right? We mean transducin's dissociating. Transducin's going to fly over here. And it's going to bind to this thing we're going to call PDE. What it means is phosphodiesterase. Okay? So we're going to go light's going to hit rhodopsin. Retinol is going to induce a conformational change. Transducin will dissociate. It will then bind to PDE, or phosphodiesterase, yes?
Is that like a protein or something?
Yeah. Yeah, it's a protein. Good question. Phosphodiesterase then is then going to activate these things over here. Now this is really where the action starts to happen. This is why cells are depolarized in the dark. It's why they're releasing glutamate all the time. And the reason is because they've got these sodium channels on the outside of their membranes. And the sodium channels are always open, which is like the opposite of what the traditional action potential model is, right? So because they're always open, sodium's coming in. Now sodium is positively charged, and sodium's always coming in. That cell's always going to be very close to zero, which means it's always going to be releasing glutamate. Which means it's always texting its boo, saying, hey, I'm here, hey, I'm here, hey, we're good, we're good, we're good. Right? Now what happens, this is a situation where light has come in though, right? So we have turned on the light. So what's going to happen? Now the reason that sodium channels are always kept open is because there's this thing that's bound to it called cyclic GMP. Cyclic, GMP. Cyclic GMP is bound and tied to this channel. Remember we talked about like locks and keys, and all sorts of ways you can have like voltage gated, all sorts of different gated channels. This is a cyclic GMP gated channel. And because it's always bound to it, it's always open, sodium's always coming in, and the cell is always releasing glutamate. Sending those graded potentials to the bipolar cells in the dark. But we have light coming in, activating this cascade of events. PDE is going to come over here. What PDE is going to do is it's going to take cyclic GMP and it's going to pull it off. Okay? It's going to pull cyclic GMP off of its binding site of the sodium channel.
That wouldn't be ionotropic, that's the...
This is a gated channel in this regard. This is a cyclic GMP gated channel. So don't worry about the ionotropic element to that for this conversation. Light's coming in, it's activating transducin, or transducin's dissociating from rhodopsin, activating phosphodiesterase. Phosphodiesterase is grabbing cyclic GMP, pulling it off of that. And what's going to happen is this open sodium channel is now going to look like this one. It's closed. What happens if this is closed? Do the sodium ions go in anymore? No. Yes. So the cell hyperpolarizes because there's no more positive charges putting it depolarized. So now the cell is hyperpolarized. It goes farther away from zero, which means it's less likely to release more glutamate, which means it has reduced glutamate when you turn the lights on. So it gets quieter, which is why your mom knows you're in trouble when you stop texting her, so to speak, with the analogy, right? That's why you know there might be a problem in the relationship when you start getting ghosted. Guess follow what I'm talking about? See how that works? So here's a tip. Go back and watch the video from this lecture and write out those steps in sequence. Step 1, step 2, step 3, step 4. Light activates rhodopsin. Conformational change in retinol. Huh? It does. It has a conformational change in retinol. And transducin will then dissociate. Transducin will activate PDE, phosphodiesterase. Phosphodiesterase will then bind and pull cyclic GMP dissociated from the sodium channel. Sodium channels close, cells become hyperpolarized, release less glutamate. Number that stuff out, know that system. And if all else fails, draw this. Trace it, yes.
And how does opsin come into this?
So the opsins, this is what, these are part of the, this is rhodopsin. This is, you can have different kinds of opsin. This is rhodopsin.
Oh, okay.
Yeah, good question. Which is why, now you can see how the genetic engineers took advantage of this to create optogenetics, right? So if we know that light will change this and open it and close it, then we can insert that through some genetic engineering to these other cells you want to turn it on and off. by knowing how those options work. Because different options are going to be differentially sensitive to different wavelengths that we looked at. Yellow, blue, right? Didn't they have halorhodopsin versus channel rhodopsin? One was hyperpolarized, one was depolarized. It all came from understanding the system. So that's a lot of information. I'm going to take a breather for a second. Sort this through.
What was PDE stand for again?
Phosphodiesterase. It's a really good tip to be able to draw this out. When you can draw it out once, then draw it out 10 to 15 more times. To where you get bored. The reason you get bored is because it's no longer interesting because you already now know it. And if you now know it, congratulations, you tricked yourself into learning it. See what I'm saying? Yeah.
I forgot the G stands for GTP,
I think it's guanol or something. You don't actually need to know what it
Is
is.
it guanosine?
Could be guanosine, but I'm not sure. Just know that it's GTP or GDP.
I know.
Yeah, we're not going to go down that road in this class. Unless you guys want to, but I get the sense that you guys feel like you've had an elegant sufficiency and anything more would be a copious redundancy.
There's a lot of words.
It is a lot of words. I'll give you a breather. I'll let you digest that for a second. That's what my grandfather used to tell my little sister when she was little. All right, we'll come up for air. We'll take a brief break from the neuroscience. Tell you a little story. So my little sister, she's now in second or third year med school, but as far as she was always my little sister. And so my grandpa used to watch her after school a lot. So she was probably in middle school, probably 10, 12, 13 years old. She'd come over and she would eat, after school snacks or whatever at his house. And he would say, "Now, Mary, one day, you might be dating some boy. And he might have you over at his house. His mom might make you dinner. And being a good host, she's going to want to make sure that she's filled up your belly and given you as much food as you could possibly eat. And you want to be a very good and polite guest. She's going to keep piling some more food on your plate, kind of like the Sugar Hill Gang song. You guys know that song? You guys know Rapper's Delight? Instead of hip hop, hip hop, and you don't stop rocking to the back. You ever been over to a friend's house to eat where the food just ain't no good? The macaroni salad, the peas are mush, and the chicken tastes like wood. And the line says, "So your friend's mom piles some more on your plate, even though you said you're good." It's like that. That's what my grandpa was talking about. He said, "No, Mary, she's going to keep piling food on your plate. You're going to be full." He's like, "But you don't want to be rude, right? You might like this boy. You want to be nice to his mom. You want to be a good guest." He said, and he had, since she was like 8, he had her practice this little 8-year-old saying. He said, "Now what you do is you say, she's going to ask you, 'Do you want some more?' You say, 'No, thank you, ma'am. I've had an elegant sufficiency, and anything else would be a copious redundancy.'" Yeah. So she's got it down. It's like an 8-year-old. He's had this like drilled into her head, like his little shtick. So I assume that you guys have had an elegant sufficiency. Would anything else be a copious redundancy? Okay. You guys want to take a 5-minute break? Take a breather. Think about it, and then we'll dive into the next section. Okay, we'll have about 15 minutes when we come back. Or 10 minutes, actually. How about that? Just take a little bit of break till it'll actually be 3 minutes. It's 37 on my watch.
So we go over
Huh?
10-minute break.
Yeah, no, we'll do it at 3:40. You have 3 minutes to digest. Sound good? Okay. 'Cause I know that I just dumped a lot on your plate. Kind of like the Sugar Hill Gang. I never got to do Rapper's Delight. That's pretty fun.
I'm starving, dude.
30 seconds. We're diving back in. All right, ready to go? Okay, so here's what we'll do. We got to slide, basically, that was slide 21. What I want to do is give you guys a chance to do some class presentations with this material and to do that next class. And so I think we can divide next class into 2 sections. One section will basically cover slides 22 through 46. And the other section will cover slides 52 through 76. So that starts about here. 22 and goes to slide 46, which is about there, to scotomas. We'll skip a few. We'll skip 47 through 51, and we'll pick up again another group, start talking about these ideas of receptive fields, and take that to slide 76, which is going to finish off talking about a spatial frequency model. So it's a pretty good bet we probably won't cover all of that, but let's be ambitious and let's aim for it. Okay? So let's try this out maybe next class. We'll have half of the class present those first section, 22 through 46. Another half present slides 52 through 76. And it should be an interactive discussion, right? So we want, just like I want you to interrupt me and ask me questions. That's the whole point of this, right? This is why that's why it's better than an online class. It's because you can stop, interrupt, ask questions, clarify if we had something, crisscrossed or something. That's the whole value. That's the whole point. That's the best part. So let's aim. We should aim for that. So don't feel insulted if people interrupt and ask questions yet.
So is half the class going to be up here?
Yeah.
So slides 22 through what?
46. The other will be 52 through 76. So why don't we go straight down the middle here? Now what you can do is you can further subdivide yourselves into subgroups to cover subsections of those slides. So a little team effort. Yeah.
So then for this side of the class, what slides do you want to do that side? I know you've divided into 2, but do you want to assign?
Let's do this side 22 through 46. And this side 52 through 76. Now think about, and I know all you guys have pretty good math skills, so realize that this is not, when you divide how many people we are, that's not very many slides that you're actually accountable for if you work together as subgroups. You have a question?
Yeah, so what if we have like a psychological condition where you can't stand in class?
Then you have to talk to me, or we'll have to work that out. Yeah. So, got about 7 or 8 minutes. Why don't you use the rest of class time to kind of talk amongst your groups, make a plan who's going to be covering what sections. You can do it together with small sub-teams. And we'll see how it works. Maybe it's a dumpster fire, maybe it doesn't work, but we'll try it out, we'll have some fun.
How many do we have? Alright, well, who's on this side? Come over here. How many? 12? What's the brain? 24?
They do have difficult.
24.
Is it 2 each?
How many groups do you want to break into?
1 view per cell, but there was 2 for science, we get 2 each.
We want to do it where it's like first two, second two, third two, fourth, and then just go on like that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then like 2 and 2. So I'm trying to make it as easy as I
So
can.
since I'm
So you get the first
I get
2,
first 2,
so
you
1,
get the
2,
next
3,
2.
4, 5, 6, 7, 8, 9, 10, 11, 12.
Okay, I came up with an idea. How about we add this layer to the assignment, yeah. Yeah. And fine, veto it, if you want to veto it, but hear me out. So for whatever subsection you're present, for every person or little subgroup's presentation of the slide, include a meme about what you're talking about.
Is that extra credit?
No, it's not extra credit. No, but make it fun. Well, that's what I'm trying. So practice your presentation skills, practice your teamwork skills, practice your communication skills, your presentation skills by connecting with the audience. Do something that will bring them in to something otherwise boring, sciencey, visual system. Make it relevant. Find a meme for whatever 4 slides you're presenting for your little section. And I don't know, just a suggestion, just a way to make it fun for you, a way to make it fun for the audience. Think of something creative connected to something real life-ish. So I don't have to keep using Drake and Sugar Hill Gang or whatever, Ryan Gosling to grab your attention. Just a recommendation. I'll just kind of put that out there. What?
So, by the time I'll be doing 54, 55.
6, 57.
58, 59, 60, 61.
66, 67.
No, it's 60. Yeah.
And I do recommend practicing to first. Hey, what's
So
up?
what should I do? Do I still do slides? Or
Do you
talk
have
to
an
SSD?
issue? Yeah, so I haven't heard anything from SSD about it, so I would talk to them about it because I'm not aware of any conditions that would prevent that. So, I would recommend, unless they would recommend otherwise, I would recommend using it as a safe opportunity to try some baby steps beyond a comfort zone, because these are things that are probably going to be some skills that might be useful at work and other stuff later in the future that maybe we can help kind of that development towards. But just see what they say. I'm happy to work with that, no problem at all. But this is a safe place. If I can make a dork out of myself.
I know, I've tried and obviously I like to
Just
talk
have a
but
meeting.
I just can't like facing that way.
Okay, well how about,
So most likely I'll have to go,
you can present it facing this way.
next, so is it Wednesday?
Or you can speak into the microphone and not have to look
If
at people.
anyone has questions, we could, like,
I would say
I'll go
this,
to
think of some creative ways
transitions or anything.
that you might be able to get around it.
What I've done before, it's too much though. One teacher made me do a video and I could like sit down and play the video.
That can work, you can do that if you want. But you can also be creative about a way you can present it. Maybe you work together with some of your teammates, and you help them to develop the slides, and maybe they orally present it.
Yeah, that's what I was
But
thinking.
this is one of the best things about teamwork, is that we can all work together and work with each other's strengths and weaknesses.
But would that be okay?
Or does everyone have the grouping, because you can start like a
Yeah,
separate.
the big picture is I want you guys to be able to work as a team. And if there's a job that you can do in the team that's very helpful, then maybe there's another job that somebody else can do that's helpful to you.
It's like a band.
Yeah, but just let me know, and we'll just.
We can start when we ready.
Yeah, we already have one.
My son had me.
I can make slides, but I can't.
I think you can not.
So what slides should I do?
Should be in.
I think we'll just let you do it, and then I can invite you to start it.
Yeah, it's like,
Do you have the, oh, you have